All right, good morning, everyone, and thank you so much for joining. This is the second of 8 webinars that the XX Network team is going to be hosting over the course of this month, divided into 4 sets. Our first 2 webinars are focused on an overview of the XX Network and our technology. The second set will have more of a deep dive into especially our consensus mechanism. The third will focus on governance and tokenomics. And then the fourth will be sort of tying it all together, making sure that we're catching any questions or topics that we didn't discuss in the first few. So thank you for joining us, and especially thank you for those of us joining us live. You'll be able to find at the bottom of your screen both sort of a chat box as well as a Q&A section. Please send your questions or comments during our presentation this morning. Our intent is to hold the Q&A, definitely answer Q&A, but keep that for the last quarter of this webinar. The rules for this conversation are very simple. First, we welcome an active and engaged set of back and forth, and we look forward to your feedback on the ideas we come up with. We ask that you keep it respectful towards everyone who's part of the conversation this morning. And second, for this webinar, we're not able to entertain any conversation or discussion of the coin sale. And so, nothing in this presentation should be taken as investment advice or a solicitation to buy anything. And again, this is not the forum for that conversation. So thank you. And with that said, let's get started here. On the second slide is our agenda for the conversation this morning. And our focus will be on covering pretty closely the contents of the XX Network white paper, which we released last week. And so if you haven't already had a chance to check that out, we recommend you do so. We've got a lot of our documents shared on the xx-coin.io website, as well as the praxxis and elixxir websites. And so we'll be going through all these topics and then definitely leaving room for questions and answers towards the end of our presentation this morning. So next, let's jump into who are we here. We've got 4 members of the team joining us in the conversation this morning. First, we have Will Carter, who's the COO of praxxis. Will is a veteran engineer, formerly with the Jet Propulsion Laboratory of NASA. He's really been leading the praxxis team in building the consensus mechanism. So we're excited to have him on the call this morning. We also have Ben Winger, who's the VP of Architecture for elixxir. Those of you who've been trying out the AlphaNet, trying out the XX Messenger, you're using the platform, the network that Ben and the team that he's been leading have built out. And so excited to have Ben on the call as well. We also have Mario Costa. He's a cryptographer with praxxis, did a lot of research with David and has been leading, again, a lot of the effort to put together the praxxis technology that really is going to run the XX Network blockchain. And finally, we have myself, Peter Somerville. I'm the head of Node and Developer Relations at praxxis. And so especially anyone who's joining this call, who's part of that node operator community or developer community, be happy to connect with you. So let's get started then talking about the XX Network. Let's begin by talking about what are the vision and the goals that motivate us here at the XX Network team. As you can see, David has been a prominent voice on the topic of privacy for 40 years. And we talked a lot about privacy here with the XX Network, with praxxis and elixxir, but how can we be a little bit more specific? What does privacy mean? For us, we think the key to privacy is not simply encrypting the contents of messages, but it's the topic of metadata. That's the who, the what, the where, the when, those kind of details about how we communicate with other people, how we interact with the world. And it's an increasingly critical part of how these digital networks observe and in some cases control us. There was a study about Facebook that I think is 4 years ago now that said, the average Facebook user, Facebook can better predict what a user is going to likely to do, their preferences, than their good friends, often can better predict than their spouse, and in some cases can better predict than you yourself. And so in that world of metadata, we need to find a way to keep that information private. And so how can we really restore that set of privacy, that notion of control to users? There's 3 key elements, and that's on the next slide here. 3 key goals which are needed. The first is you need functionality. You need a network that can, in fact, protect that metadata for users, protect their privacy. You need robustness, and you need performance. These are the 3 kind of focuses that are animating our work here at the XX network. And they're what we think are really exciting innovations that we're bringing forth here. So first, in terms of functionality, you have to shred that metadata. You need to protect that so that the users have that envelope, that kind of bubble of privacy around themselves. And that comes not just to payments, not just to cryptocurrency transactions, but to messaging and your communications. And that includes DApp or application communications. It does include the payments, and it also includes voting. If you're going to have a truly decentralized network, you need to have a robust voting mechanism that's going to really work. As Mario will be getting into in the governance section, probably in the second half of this talk, this is actually an area where our team has a lot of credibility, a lot of experience. On the question of robustness, you need to be, if you have the world's best privacy protecting technology, you need to also make sure that it can withstand attacks. And that includes quantum resistance, protection against quantum computers in the future, or the strongest organized attacks in the present. You need to resist against a money attack. Proof of stake networks can be vulnerable to, those whales who can, what are the financial resources that are brought against a network. You need protection against a civil attack, and you need to resist attacks based on the voting system that a network has. And the third key factor is performance. If you've got this wonderful network, but it only can be used by a few people at a time, then you're not really bringing these capabilities to all. And so on the next slide here, you can see that performance is about linear scalability. It's about what's your throughput of the system. And so those are the 3 key features that we'll be talking about as we cover across the spectrum here for the XX network. And so let's now dive a little bit deeper into the details. I'm going to hand the microphone over to my colleague, Ben.
Hi. So I'm going to kind of give you the basic overview of what is the XX network. And it's a question that has multiple answers, like any good question. From the question of how we're building it, the XX network is the combination of the technologies of 2 different organizations, both led by David Chong. So one of those is elixxir. I'm a lead engineer at elixxir, and we are building the privacy protecting metadata shredding mixing layer of the network, which is based upon a protocol called CMIX. And then there's praxxis, which is led by Will Carter, who's also on this call, who is, or not led, operated by, which is building the XX consensus mechanism and the blockchain of the XX network. And together we're creating a singular platform. And then there's another question of kind of technically what is this thing? And here's kind of the highest of high level diagrams of the network. So as you can see, the network has a team of nodes called the mixing team, which is able to process a batch of messages. What this team does is it does the actual privacy metadata shredding operation, and further in this presentation, I'll get into the details of how that works. Once they complete, they pass off the data to the block producer, or messages are simply delivered, and this mixed payments are already anonymized, and now they're used to produce a block, which the block producer produces. Endorsers endorse, a process which we'll dive into a little bit more, and the block is added to the blockchain. There's something I would like to point out, which is if you look at the center node on the mixing team, this shows actually where our logo comes from. It's not just a pretty set of two X's. It's fundamentally descriptive of our core technology, which is mixing, or one of our core technologies. And I guess I'll pass off to William Carter.
Thanks, Ben. So I'm actually going to talk about two things. I'm going to talk about the XX coin, which is the most advanced, private, and secure cryptocurrency, or currency for that matter, in the world. And then I'm going to dive into a little bit about the XX consensus mechanism, which is the only consensus mechanism in the world that has the speed, scalability, and security to both support that cryptocurrency and to build platforms which can replace the centralized platforms that we rely on a day-to-day basis. And so first we're going to start with the XX coin. And when setting out to design the XX coin, please go back. Thank you. When setting out to design the XX coin, we had a list of requirements that we needed the XX coin to kind of fulfill and to really be a currency of the future. These fall under some of the requirements that Peter laid out earlier. That is security, privacy, and usability. And I'll dive a little bit into these and how we achieve them. But first, what is the XX coin used for? So in the XX network, the XX coin is used to compensate the developers and the node operators. It takes time, money, and effort to run a node. And so this is how we incentivize the community members to take part in running the network, to provide robust and performant nodes. It's used to incentivize governance, which we'll talk about a little bit later. But our platform is unique in its ability to incentivize the community to privately and securely participate in the governance of the network. And it is the primary vehicle for exchanging value in the XX network. And this is really what kind of started the blockchain movement, being able to create a mechanism to exchange value across borders and outside of the control of the centralized institutions that currently control our transfer of value systems throughout the world. So next slide. So now I'm going to talk a little bit about the goals we've set out to achieve here, starting with security. And obviously, real security is being stored in this network. And so we need to not only protect against the threats that we currently face, but also threats that are in the near future. And quantum security is something that you'll hear a lot when you read anything about praxxis. We actually have an entire blog series about this that I recommend you go read if you're interested. But quantum security is important because most of the cryptography that is currently used to secure the wallets in any blockchain platform out there can be fatally broken by a sufficiently powerful quantum computer. And this not only is limited to blockchain platforms, it extends to many of the secure data infrastructures that you interact with on a daily basis on the internet. And so we don't think this is necessarily a threat in the next year, but we have seen a lot of development and investment in this space. And the problem with this is when it does become a problem, we likely won't know about it. This is something where the value of breaking public key cryptography lies mainly in your ability to leverage it without other people, before other people know about it and start protecting against it. And so, building a cryptocurrency or a currency of the future means that it should be able to, it should be built to already withstand the attacks of a quantum computer. And retrofitting a blockchain to be quantum secure is not a trivial task. And unless you've designed around the limitations that quantum secure cryptography introduces, you're going to hit major performance hurdles. So retrofitting some of the existing blockchains with quantum secure cryptography is not going to be a trivial task. And so we've gone ahead and integrated quantum secure cryptography from the beginning. We do this using one-time use hash-based signatures, which I'll talk about a little bit in the next webinar. And we use a specific version of that called Watts Plus. Next slide. Okay, so there's roughly at least three ways we want to enable users to send XX coin through the network. And before I go through each of these ways, I wanted to go through two of the other goals. I already went through security, but privacy is also a very important goal for us with the XX currency. Data is power in the digital world, and many centralized organizations have more or less proven themselves to be untrustworthy of that data. And in order to put you back in control of your information and data, we have to make that data private when it's when it's being exchanged between parties. And this is particularly important in payments because what you're willing to pay for says a lot about you. That saying about put your money where your mouth is. If you're willing to pay for something, that means it's probably something that's particularly valuable to you. So we definitely want to provide privacy in the payment space. And we also need it to be usable. That's our third goal. We need it to be able to fulfill a variety of use cases, and we need it to be fungible. And we'll talk about that here. So the first structure or the first way that we want to enable people to send money through the network is denominated coins. And these are a very similar to physical currency, both in form and function. Like physical currency, they have limited static values. And also like physical currency, they are private when used. And this is why we use denominations, because denominations split highly identifiable transaction values into uniform subtransactions. So instead of seeing the value $3.19 for a latte, you just see a one, or if we translate that over into XX coins, 3.19, you see one XX coin, one XX coin, a 2XX coin, and a number of fractional XX coins that are mixed in with uniform sets of similarly denominated currencies in that batch. The way I guess I would describe this as an analogy is if you go to a store and when you buy something, you just put a bunch of cash in a box. And everyone does that throughout the day. And then at the end of the day, they're left with a box of denominated bills. And they have no way to link which one of those dollar bills came from which purchaser. And so that's kind of what we're doing here. And this is what enables, when used with elixxir, this is what enables the privacy that we're trying to achieve. The next core data structure or next core coin structure we want to offer is wallets. And one of the main kind of limitations of denominated coins is that they can only be used once, which makes non-interactive payments difficult. I can't give my employer a single coin address, which they can deposit an arbitrary value of XX coins into every other week. Denominated coins can only be used one time, and they're only good for the value which they've been minted for. They can be traded for smaller denominations, but generally, if I want to give someone an address and continuously receive money into them, I need something that can hold an arbitrary value. And so that's where wallets come in. These are very similar to what you'll see in other cryptocurrencies. And these are a little unique in that the quantum secure cryptography we use is one-time use, which means, once you use it, you have to build a new public key and a new set of private keys to sign it with. And so we had to kind of create some novel structures to enable this, which we'll talk about, at a later time. But one of the side effects of wallets is that it has reduced privacy. So we're able to use it multiple times. It's able to store arbitrary values, but it does have reduced privacy because it doesn't have those uniform denominated values. And then lastly, we want multi-signatures. These are either denominated or wallet-based, so they can be coins, they can be wallets. But these are characterized by the requirement for at least 2, or whatever the threshold you set, parties to sign it. So say you have an organization of 3 people, and the currency is private, so you don't want one person to be able to run off with all the money. So you want at least 2 people you want to require at least 2 people to sign off on a transaction before it's valid. So that's where multi-signature comes into play. And again, we'll talk about some of the technology that enables this at a later date. But these are the major kind of coin structures that we want to enable people to use when they use the platform. Next slide. All right, so this is the XX consensus mechanism. I'll go first a little bit into kind of what it is we're trying to achieve. Next slide. Yeah, so when we set out to identify a consensus mechanism, being that the XX platform or the XX network is decentralized, it obviously required a decentralized consensus mechanism. And so we had to identify a set of requirements that this consensus mechanism needed to achieve in order to be usable for our platform. The first being kind of speed, both in finality and in throughput. And the currency of the future can't be slower than what we're accustomed to today. Nobody wants to wait hours or even minutes to buy things. And also our goal is to offer a platform where developers can create alternatives to many of the centralized platforms that we use on a daily basis. And so we need speed and throughput in order to make these apps responsive. We also need this, scalability. So this is largely to support the ethos of decentralization. You want a large, diverse node community so that the community can take part in the ownership and operation of the network. But this also supports the next goal, which is robustness. And this is robustness against attacks both from within and from without. This could be Sybil attacks, malicious nodes, malicious clients, or even an unreliable network, and even attacks from nation-state adversaries. And then finally, we've already talked about this a little bit, but there is a weak link aspect here. We need it to be quantum secure. It is useless to have a quantum secure coin if you don't have a quantum secure consensus mechanism, keeping the operation of the network similarly secure. Next slide. So with these requirements in mind, we kind of took the first thing we did was we took a look at the frankly, hundreds of consensus mechanisms out there. And there had to have been one that could meet these requirements. And what we found is actually there were none. There were no consensus mechanisms or platforms out there that really met the requirements that we saw were necessary to really make blockchain a mainstream technology. And so, if you look at this, you can see that generally there's trade-offs in all these approaches. Bitcoin and Ethereum, slow, they have high latency, but they are very scalable. BFT consensus mechanisms like Tendermint, LibreBFT, and even Algorand, characterized by pretty quick consensus operations. They're not forkable, but they're also not very scalable. You generally don't see them with more than 100 nodes. And then you have DAG-based consensus mechanisms, kind of like Avalanche, where they are extremely fast, extremely scalable, and not forkable. But then if you have significant Byzantine presence in the network, they get exponentially slower over time. So we took a look at all these and we decided it looks like we're going to have to make our own consensus mechanism. And that's exactly what we did. Next slide. And so we made the XX consensus, and we were able to achieve a couple of unique and important properties, which we've laid out here. The first of which is constant transaction communication complexity. And what this means is, or the best way to visualize this is when you send a transaction in most consensus operations or protocols, it needs to be gossiped throughout the network. So if you have 10,000 nodes, it needs to be gossiped to some threshold, some majority of those 10,000 nodes, and this takes a long time. What we've been able to do is fix that, the number of nodes that a transaction needs to be gossiped to a constant value. So whether you have 100 nodes in the network or 10,000 nodes in the network, your transaction only needs to go to, say, 200 of them or 100 of them. Similarly, linear authenticator complexity means that as your network grows, the network bandwidth requirements or the network resource requirements also only grow linearly. We'll talk a little bit about this in the next webinar, but this is extremely important to reaching mainstream adoption and having a decentralized network of many thousands of nodes. The third is egalitarian consensus. This is distinguished against maybe proof of work or proof of stake algorithms that you might be familiar with, in that every node in the network has an equal opportunity to participate in being a block producer in the network, which means, you know, they get a block reward from producing a block. And this is important because it prevents a concentration of wealth or a concentration of, say, hashing power from creating a centralized power in the network. And so we'll talk about that again in the next webinar. Probabilistically unpredictable scheduling. This is what enables unmanipulatable randomness is before that. Unmanipulatable randomness is extremely difficult to achieve in decentralized networks. We'll talk about how we achieve this in the next webinar. But this allows us to do our egalitarian consensus operations. And also it allows us to do the next thing, which is the probabilistically unpredictable scheduling. This is important for robustness. If an adversary can't tell when you're going to be scheduled to be a block producer or an endorser in the network, or even a CMIX node for that matter, their ability to attack and delay you is dramatically reduced. So this is important for robustness. And then finally, we have created a novel, compact, quantum secure proof of finality. This is important in the age of mobile computing, where you have limited bandwidth, limited computational power in your smartphone. And generally, quantum secure cryptography is quite data intensive, so these signatures are large. We don't want to send massive packets of data to phones in order for them to be sure that their transaction is final. So we've developed a way to shrink the proof of finality, which smartphones can use to verify that their transactions are completed, into something way more manageable. Next slide. And we've done that using 5 key approaches. I'm just going to gloss over these in this particular webinar because we will dig into them in detail in the next one. But the 5 key approaches we've used to kind of achieve these properties are NodeCon, which is a physical event where the network is initialized in a quantum secure manner. And this is by having people meet in person, exchange symmetric keys, and collectively generate a random seed, which will be used throughout consensus in the network. And that's what's used to seed the next approach, which is commuted randomness. I talked about this on the last slide, but this allows us to generate an unmanipulatable random every block by chaining secret but committed values that each block producer reveals when they're up as a block producer. And using this committed randomness, we are able to randomly select a sample of endorsers every round. And this is what allows us to do the constant transaction scalability that I mentioned earlier, in that it allows us to select a constant number, say 100 nodes, to receive, verify, and endorse the transactions in a block, which prevents us from having to gossip a transaction throughout the network. Efficient fallbacks, every once in a while consensus is disrupted, and that could be from unresponsive nodes, it could be from an unreliable network. Regardless, we want an efficient way to fall back and recover. And we have kind of a novel, what we call bistable framework in order to achieve this. We'll go into this in the next webinar. And the next one is compact endorsement. And as I already mentioned, this allows us to generate a compact quantum secure proof of finality. And this is particularly important, not only for consensus performance, but also for enabling mobile devices with limited bandwidth to verify the finality of the transactions that they submit. And using these 5 key approaches, next slide, we have created the only consensus mechanism in the world that we feel meets the requirements to really make a platform capable of replacing the centralized platforms that we use on a daily basis. And that's it for consensus.
Great. Thanks, Will. So let's talk a little bit about the role of nodes within the XX network. I mean, they really end up serving as the backbone of this network. And so if you go to the next slide, 2 key questions emerge around nodes. First of all, what are nodes within the XX network? And second, what do they do? So we envision nodes within the XX network as a global decentralized network. Our expectation is that the mainnet will have thousands of nodes throughout the world, and that they'll be using equipment that's pretty widely available. Our goal, part of the vision for the XX network is that if your server requirements are so extreme that you end up with most of the world's nodes kind of living in 3 big server warehouses, then you really haven't achieved decentralization. And so the nodes will be chosen through the governance process that Mario will be discussing below. Part of their work is that they'll be incentivized in XX coins, both through block rewards and inflationary rewards. They'll be investing their time and effort and some money in running a node, and we need to make sure that that's a worthwhile experience for them. And some of the initial nodes will participate in NodeCon as we get the network up and running. So right now we have the XX Network AlphaNet running. That's a series of 8 professional node operators that we've contracted with. Once we get to the beta net, we'll be making use of the 600 beta net nodes who were chosen through a process that we ran earlier this year. This was something where our hope had been that we'd get 100 or maybe even 200 decent applications to run this run on the beta net. We were really blown away. We got more than 850 applications from 80 plus countries all around the world, most of which were of a really high quality. And so we're really excited to start working directly with these XX network beta nodes. And then after the beta net, with all the lessons that we learned from the beta nodes, we'll be turning over to the main net. And so what do these nodes do? One of the kind of key understandings, there's not going to be some nodes over here running elixxir, running the CMIX protocol, other nodes over yonder running the praxxis XX consensus. All nodes will be doing both. And so each node is going to be both members of mixing teams, running the CMIX protocol, doing that work. And then they'll also be helping to run the XX consensus, again, taking turns as randomly chosen as both the block producer and as part of that set of endorsers. And so we'll be getting into details with that. And again, I personally am really looking forward to kicking things off with our BetaNet node team early in the new year. And so we'll get a little bit in the timeline later in the slide deck. But for now, I want to hand things back over to Ben to talk about communication on the XX network.
Hi, Ben here again. So we're going to talk a little bit about the XX communication, which is the privacy layer of the XX network. So XX networks were first introduced by David Chaum in 1979, and then a more formal technical paper in 1981. And mixed networks to this day remain probably the most secure mechanism for building an anonymous communication protocol. And the way they work is essentially you just forward a batch of messages from server to server. And as you can see in the bottom diagram, each one reorders them. And what as you can't see is that they're re-encrypted or decrypted so that you can't correlate numerically input to output. And then once they get to the end, they are kind of fully decrypted and the information necessary to deliver them is made available and they're delivered. The fundamental problem in this approach is that all of these encryption operations are blocking relative to each other. You have to mix and decrypt the entire batch of messages before you pass it on to the next node. And the same thing and the same thing. So what ends up occurring is that these time-consuming public operations end up taking a very long time, and the latency of passing data through a mixed network of sufficient size to really be valuable. So, you know, this example has 3 that wouldn't give you much anonymity protection. Sufficient size is hundreds of thousands to millions. And once you get to that size, the speed of these networks is too slow to be functional, or historically they have been. So as a result, the world has come up with other alternatives that don't have as good security properties, things like onion routing and other structures. So in 2016, David Chaum came back and published his paper on CMIX. And CMIX is unique because it takes this mixing structure and it enables it to run at reasonable speeds by taking those complex computations and figuring out a mechanism to execute them before the messages are received. And as a result, while the network still has to do the computation, the users of the network don't experience the latency resulting from it. Now, elixxir has been working to implement its variant of CMIX, which integrates full end-to-end encryption and is able to defeat not just the basic idea of mixing, but also further mechanisms of metadata analysis. So one of the other things that can occur is that if you don't have ununiform packet sizes can be used to figure out what's going on. So if you see a packet at exactly 93,124 bits going on one side, and then somewhere else you see a packet of the other size come out, there's no other packet of that size, well, you're likely to be able to figure out the two are the same. So CMIX breaks up packets into uniform packet sizes so that such attacks can occur. The other problem is packet timing, which is that if packets come in at a certain time and then leave at a certain time, even if they're kind of jumbled with other ones, you can kind of figure out which one is which. So CMIX uses this batching process whereby messages are processed as a large group, which eliminates timing issues. So by combining all these things and combining pre-computation, we've delivered a network which actually you can use right now with the XX Messenger in its alpha state, which is able to anonymize messages with relatively low latency costs. The network as it stands, I think, has 6 seconds latency, although the current structure doesn't take full advantage of pre-computation, and we expect it to get down to possibly 1 second by the time of BetaNet. I want to go back because we have a question here about if the database gets compromised, and this really answers the question, which is that every single node would have to reveal how they mixed messages and how they encrypted them in order to de-anonymize messages. And that's fundamentally how we answer this question, which is that there isn't a singular database. There's not one place which would have to be compromised. So we have here a kind of example of a mixing network and how the anonymity works. So as you can see, you have in this a 3-node setup, and 2 users are passing money into the network to be exchanged. And the coins passed in are mixed together, and the BP cannot tell which coin is which, where they came from, or even how they correlate. So the blue individual in this case sent 6, but the BP can't tell, and also can't tell where it came from. And also we can't either, because we can only see the central node. In fact, if we can only see one node, we still wouldn't be able to see where money went or where it came from. So it's a fairly powerful technique which is able to scale to thousands and thousands of transactions simultaneously at relatively low cost. So we're going to hand off to Mario, who's going to discuss our governance infrastructure.
Okay, so let's now approach. Sorry, 1 second. My bad, we had a couple of issues here. All right, so let's discuss governance in our system. I'm just going to give you an overview of what we have going on here. We have very interesting material here to present. We even have a webinar completely dedicated to this. So I think you guys are going to love what we have for you. So the most important thing to highlight here is that for a blockchain to be robust, it cannot allow any type of manipulation by entities with a lot of money. So what does this actually mean? So a blockchain needs a strong governance that allows a platform to update either the code base, the data structures in the platform, or even the network. Let's say we want to add new nodes. Usually how you do things is you have one user, one vote. Now, this is way easier said than done because it requires everyone to vote. And as we've seen on other platforms, what usually ends up happening is a really low voting turnout. So another problem that appears with this solution is that the parties with a lot of money can start buying votes to manipulate the decisions of the network. And if you don't really solve this properly, you're essentially back to square zero because you're a proof of stake platform. Can we go to the next slide, please? So here we're just showing exactly like the role of governance in our system, the type of changes that we envision that will probably take place. So we will be adding new nodes, removing new nodes, adding more sources of user identity, even like potentially changing the software of the network. And then the proposals that take place in the platform actually change according to the importance. So we might have to like apply changes to token economics, change to governance, and like the platform supports all of these changes. Let's go to the next slide. All right, so to properly solve this governance problem, we need a system with secret ballots that scales with the complexity of the issue. So for example, a small code base should only require a smaller number of voters than, for example, changing the entire block structure. On top of this, we need to stop vote buying. And we actually have that. We call it random sample voting. It was introduced by David a couple of years ago. It's purely peer-reviewed. It has already been used, as you can see here, at the World Forum for Democracy in 2017 in France. And I'm actually going to explain in the next slide how this process actually works. So first, we require a good random beacon. And turns out we actually have that. As we'll explain in NodeCon, we have very strong randomness that allows us to select small committees to make very important decisions in our platform. So using this voting mechanism, we can actually solve the key turnout issue because we have way less voters to take very important decisions in our platform. The team in our company has already run many elections previously. One example, was an actually US election in Tacoma Park in Maryland a couple years ago. Next slide. So how do we stop vote buying? We introduced the notion of decoy ballots. How do these ballots work? These are completely indistinguishable ballots that any user can request and then sell to whoever is trying to buy votes. So essentially what this allows is users to sell votes that will not be counted in the actual election. So you're basically mitigating any buying efforts because the vote buyers will just literally be spending money. There are multiple papers that support that this is actually a very efficient solution. We are presenting here one of them. This is extremely interesting material. And it's very important to mention this in our platform because this is also part of the incentive model. You are not only incentivized to vote, but you ironically are also incentivized to sell votes because you can sell fake votes to vote buyers while keeping the integrity of the elections.
Hi, Ben here again. We're going to talk a little bit more about the token economics of the network. So, as most networks, we've got a block reward. It's comprised of two parts: income generated from fees like paid messaging fees, and inflation designed to cover operating costs. In general, the inflation is designed to cover the majority of operating costs, while the fees are generated, to be more of income for the network. It's important to note that a small portion of block reward goes to governance to incentivize voting. Part of the voting mechanism is that because of the small number of votes, you can actually pay people to vote, either through just straight payment or through a lottery. And part of it is also to ensure that the network is developed into the future. We have token distribution we've announced. I'm not going to say much here. I'm just putting it up here because it's a part of our network. You can find more information for non-US individuals on the XX Coin website. There's another really important part of our economics that we want to discuss, which is the economics of the XX network's communication. So if you look at the elixxir architecture paper, we go into details about how the mixed network scales. But I'll give a quick primer on it. So essentially, blockchains generally, as you add more nodes, get slower, or at least they never get faster. But that's not true about mixed networks or communication networks in general. So the communication layer doesn't fundamentally have a problem with double spending. You don't need to compare every message to every other message. They're encrypted anyhow. You couldn't if you wanted to. And as a result, as you add more nodes to the network, more teams can be formed and more throughput can be added, which creates a very, very nice economic loop where as more users use the network generates more revenue. It can afford to onboard more nodes, and as it affords to onboard more nodes, it can increase capacity, which allows more users to use the network, and it creates a virtuous cycle, which continually brings the network up, increasing its utilization. It's very important that the cost of the network doesn't increase as more people want to use it. In fact, if anything, the cost will decrease, although we can't make any promises. And that's it. So in the third webinar, we're going to go into more details on this, and we're working on a paper which will have more details on this process and other things in tokenomics, which we hope to release soon. So I'll pass off to Peter.
Great. So the last thing to discuss before we go into Q&A and answer your questions is just to give you a sense of our milestones. What's the timeline looking like for the XX network? And so you can see here on the next slide, there are four main phases leading up to the real deployment of mainnet. We had an internal test net, we had an alpha net, and that's where we are right now. They're in the second of these four phases, reading left to right. We'll have a beta net and then a mainnet. And so as you go left to right, you have increasing scale, increasing complexity, and also increasing decentralization. The internal test net consisted of 3 computers that we owned, right? The AlphaNet, currently there's 8 node operators where we're paying them directly for their work for us, but it's computers that are out of our hands. And they've been doing a great job for us here. The BetaNet, again, that's going to be 600 nodes that we invited a great deal of public input in selecting them. And then the mainnet, that's going to be a decentralized network of thousands of nodes chosen through the governance process of the XX network. And so it's only been a little bit over a year since elixxir was first announced and the testnet demonstrated. In that time, again, we've selected the BetaNet nodes. We released the XX Collective app. announced the Aero SDK, the developer toolkit for dApp developers, announced praxxis, put the AlphaNet out into the world, and also released the XX Messenger. We're continuing to work through that waiting list. I think we've got several hundred, close to 1,000 users with access to the XX Messenger. My expectation is that we're going to have just about everyone who's got a number on that waiting list able to use it within the next month or so. If you haven't done so yet, we encourage you to download that XX Collective app for your Android or your iPhone. Get yourself in the queue to get access to that XX Messenger. Looking forward, we expect early in the new year, we'll have a detailed timeline leading up to the launch of the BetaNet. That's when I'm going to be, probably Ben and I working pretty closely with those BetaNet node operators, applying the lessons we've learned here through the AlphaNet. And then that's going to lead up to later in 2020, the release of the mainnet. And that's not the end of this story, by the way. We expect to be doing quite a bit of development work off into the future there through that mainnet. But our focus is leading up to getting this mainnet launched and really bringing all of the properties, all the technologies that we've been describing here today, and being able to put them in the hands of everyone who's excited about the goals that we're pursuing, giving them those capabilities. And so it's really exciting to see the enthusiasm of the global community and to see so many folks turning out for these webinars. At this point, let's start looking at your questions. Thank you for submitting these questions, and we're going to start working through them here.